This tutorial will illustrate some of the options available when modeling walls in ETABS, namely meshing, adding and opening, and assigning pier and spandrel labels. As discussed in the drawing tools Watch and Learn, there are a number of different ways to draw wall objects. The focus of this tutorial will be to discuss the options available once the walls have been drawn. First, we will show some of the meshing options. We will select a wall object and then go to the Assign Shell Wall Auto Mesh Options command. The default setting is that the straight walls are not meshed. The physical object and the analytical element are the same. However, there may be times when meshing is desired, and ETABS allows the user to select the meshing. One option is to specify the number of vertical and horizontal elements. The user may also specify an auto rectangular mesh. If we select another wall object and then this option, the Modify Show button shows that the mesh size is set to 4 feet. Here we will reduce it to 2 feet. Note that this setting applies to all shells assigned the automatic meshing option. Note that the assignments are shown on the wall objects. If we go to the Set Display Options form, we can have the actual mesh displayed. Again, the default is no mesh, which typically gives good results due to the sophisticated finite element formulation of the wall objects. The good performance of the unmeshed walls can be observed by reviewing these side-by-side walls. On the left, we have meshed the wall objects into 2x2 elements, and on the right, we are using the unmeshed default settings. We have applied a 25 kip lateral load at the top of each wall. After running the analysis, a right click on a top joint shows that the wall on the left has a deflection of 0.020378 inches. And the wall on the right, a deflection of 0.019619 inches, a difference of only about 3%, well within engineering tolerances. However, there are cases where proper meshing is very important, such as modeling walls with discontinuities. Here we have a planar wall with an offset at the first level. The load on the model will be a static earthquake lateral load. It is the connectivity and behavior at the offset corners that is of particular interest. If we run the model with the default no meshing assigned to the wall objects, we see that the structure is unstable. This is not an appropriate model. To rectify this situation, we will modify the model in 2 different ways. In the first analysis, we will use a refined mesh with no edge constraints. This will be the standard for comparison. In the second model, we will use a semi-refined mesh with connectivity at the corners along with edge constraints. For the first analysis, select all of the wall objects and assign an internal mesh of 1x5. reselect the wall objects, and turn off the edge constraints option. If we go to the Set Display Options command, we can view the mesh on screen. Note that the mesh lines up not only at the corners, but that all of the interior mesh lines are continuous. Next, we rerun the analysis, and a right-click on a top joint shows a displacement of 0.014. Note this for further reference. A plot of the forces in the wall shows a pattern that seems appropriate with the expected concentrations around the corners. In the next analysis, we will use a mesh that does not line up in the interior region, but does provide connectivity at the corners. Select an object and assign edge constraints, making sure that the Apply to Full structure is checked. This will help to lock the mesh together in the interior of the wall where it does not align. Running the analysis this time gives a displacement that is approximately only 5% different than that for the refined mesh. And a force plot that is reasonable. Thus, this is an effective use of the edge constraint option. Using a mesh and edge constraints is a powerful feature for connecting walls with discontinuities. As a side note, had we not used the edge constraints to tie the two meshes together, we would have had a sizable gap where the two misaligned meshes meet. However, with the edge constraints on, the objects are tied together even though the meshes do not line up. Next, we will show how to draw an opening in a wall object. This can easily be done using the Draw Wall Openings command. Clicking on this displays a properties of object form with width, height, and distances to the first corner. Note also the lock icons. We will explain these in a moment. There are a number of ways this command can be used. The first can be done without entering any values in the properties of object form. Make sure that the locks are unlocked, and then click on the wall object that will have the opening. This displays the dimensioning lines. The next click locates the first corner of the opening. And the third click sets the opposite corner and finishes the opening. Note that the size of the opening is displayed in the properties of object form. If we lock the size dimensions of the opening just drawn, the first click on a wall object will again display the dimensioning lines, but the size of the opening is now fixed. A second click completes the drawing of the opening. Lastly, if we enter dimensions for the bottom left-hand corner of the opening, and then lock these dimensions, a single click on a wall object will draw the opening at the specified location, regardless of where we click on the wall. We could also unlock the width and height dimensions, but leave the corner position locked, which results in the starting corner being locked, but allows the size of the opening to be dynamically adjusted. We can also add openings by eliminating sections of walls using the Draw Reference Points and Draw Reference Planes commands. Here we have a building where the elevator core walls have been drawn, but with no door openings. To get a better view, we will activate the 3D view and select the walls. We can then right-click away from the model and choose Show Selected Objects Only. We want to add 2 doors per story along grid line 2. Switching back to the plan view, we right-click again away from the model and select the Snap Options command. Set the Plan Fine Grid spacing to 48 inches and check the Fine Grid option. This will allow the cursor to snap to points 48 inches on center anywhere on the plan. Now, click the Draw Reference Points command, and we will add reference lines along the grid line 2 walls at the fine grid points. We can see these reference lines better if we switch to an elevation view. The next step is to add reference planes to mark the top of the door openings. Our doors will be 8 feet tall. We set the vertical offset to 8 feet or 96 inches and click once at each story, starting at the base through story 4. If the locations of either the reference points or planes needs to be reviewed, this may be done by going to the Edit Stories and Grid Systems command and clicking the Modify button and then the appropriate reference button. The next step is to divide the walls up into sections that match our reference lines and planes. Select all the wall objects along grid line 2 and go to the Edit Shells, Divide Shells command. Here we select the intersections with visible grids option. Now it is simply a matter of selecting the wall objects where the openings should be. And then deleting. Next, we will assign pier and spandrel labels to the wall objects. These labels must be assigned before we can obtain either output forces or design the objects. Piers will report the forces and perform the design at the top and bottom of each object for each story. Spandrels, on the other hand, output the forces in the design at the left and right ends of the objects and not the top and bottom. Objects may be assigned both the pier and spandrel label, but no object may have more than one of each. There are many ways to arrange the labels, and we suggest you review the shear wall design manual for more details. A right-click on a wall object shows that initially it is not assigned either a pier or spandrel label. To assign a pier label, simply select the wall objects and go to the Assign Shell Pier Label command. Here we can use an existing label or create a new label. If we run the analysis, we can display the forces based on the pier labeling. And then run the design. This was a simple wall and pier arrangement, and next we will look at a more complex wall layout. Here we have a wall system created using the wall stack feature. Unlike the other wall drawing commands in ETABS, when drawing wall stacks, pier labels are automatically assigned. We can see the pier labels by going to the Set View options, and on the Other Assignments tab, clicking the Labels checkbox. In this case, P2 was assigned. Note that the wall stack command assigns the same label to all walls in the stack. The analysis has already been run, so we can go straight to the shear wall design. Note that in the 3D view that the reinforcing is reported at the centroid for the entire section. That is, the total reinforcing required for the 3 wall sections as a whole is reported, in this case 10.08. A right-click displays the pier reinforcing report. However, it might be useful to know the reinforcing required in each of the 3 wall segments and not just the total. To do this, each segment should have its own pier label. We will assign the 2 vertical legs different pier labels. We will create a P3 label and then a P4 label. Assign them to the walls. And then rerun the shear wall design. On the 3D view, we now have 3 different reinforcing values reported, one for each wall segment. Although the 3 different values shown total up to the number previously reported, we now have a better understanding of how the reinforcing should be distributed throughout the stack. Lastly, let's look at the pier labeling when openings are present. For this model, we are going to assume that we want the wall objects on the left of the openings assigned one pier label, and the wall objects to the right of the openings assigned another pier label, so that we will have design output for each side. An alternative labeling scheme would have been to only assign pier labels to the wall objects that lie directly adjacent to the openings, so that reinforcing would be reported at the top and bottom of the openings. For the wall objects directly above and below the openings, we could assign another pier label, or a spandrel label, or both. In this case, we will apply a spandrel label, which will provide us design results for these shells in terms of spandrel behavior. We run the analysis, and then the shear wall design. The longitudinal reinforcing required for the walls on each side of the openings is displayed. If we go to the design menu, we can display the spandrel reinforcing. A right click on a spandrel displays a report showing the particulars of the spandrel design. With design complete, we can go one step further by running detailing. Based on the design reinforcement calculated and the detailing parameters, schematic drawings are generated. This concludes this tutorial on modeling walls.